Hi team, welcome back. First episode went down really well, all about condensation, and as I said at the end of that video, I'm going to break down the next really important concept, which is that of dew point. Now, this is nothing to do with unpaid bills, but this is all to do with the dew point temperature at which water turns from a gas into a liquid. I'm going to unpack that more in this episode. Now, to kick off with, we are going to have an assumed level of knowledge here. So this is about condensation and the fundamentals of how molecules of water, when they lose their energy, clump together and you can see them as fog. If that doesn't mean anything to you, go and check out the video, which I'll link up here, which is the first video I did to explain that, because that is an assumed level of knowledge we'll need for this video carrying on. Just before I do move on, I'm going to make the point though, and I saw this come up a lot in the comments, was what I'm trying to get across here is the fundamentals of physics and the understanding of what happens in our buildings so that you can make an informed decision about what works for you. This is not me saying you must do this, or if you do this, this will happen. Every house is different. Everyone living in their homes are different. Everyone has a different way that they deal with these kind of situations. And so what I'm trying to do here is get across the understanding of what's going on so that you can make the best decision for what works in your home, whether that's a dehumidifier, whether that's opening windows, whether that's running a tumble dryer to dry your clothes versus airing them inside. Every house is different. You need to find your own way. This, I hope, will explain why we get issues sometimes and how you can then potentially deal with them. So specifically now, what does opening the window on a cold day do? Well, it changes the air mass. So the moist inside air moves outside, the colder, drier air comes inside. But so what? Why do we want to do that? Yes, we want to get rid of the moisture, but what's the difference in having a dry air versus a moist air? Well, that's all to do with this concept of dew point. Now, I've got a really nifty way of demonstrating and showing this visually by taking you to my bathroom, turning off the extractor fan, and having a shower. Now, I need to be a bit careful with camera placement to keep this family friendly, but the visuals should help. And yes, I am a bit of a loser. I do have a hygrometer in my bathroom. So whilst I'm busy lathering myself up and washing what little hair I have left, I thought I'd introduce you to another little gadget. So whilst I have said these are absolutely essential for understanding your humidity, aligned to this video is this device. Now, quite simply, it is a infrared thermometer. So you point it at something, it's got a little laser pointer on it, pull the trigger, and it gives you a temperature reading. Now, you can go around your house, essentially, and point at surfaces and get a reasonably accurate, not perfectly accurate, temperature reading. It has to be held a set distance away, so I think it's something like 12 centimeters away, to get a rough temperature reading from that surface. So I'm going to use that now for the rest of this video. Now, without the extractor on, look how steamy it gets in here. When I take a spot measurement, you can actually see the laser beam through the steam. Pretty cool, eh? Here's the other thing. This bathroom mirror, I actually rigged up with a heater demisting panel rigged up to the extractor fan. So when I turn the extractor on, it will actually heat up this part of the mirror, which reduces the condensation. Now let's go and turn the heater demister on. So whilst the mirror is doing its thing, let's now calculate what the dew point temperature is for the air in here. You'll recall from my first video showing you the free online dew point calculator online to do this. So heater demister done its job now, and you can see where the condensation is just around the outside where I don't have the heater demister. Let's measure the temperature now. In the center, 20 degrees. Outside the center, 17.3. Now we know the dew point temperature is 17.5 or 17.6 roughly. That's why I've got condensation where it's cooler. So I'm out the shower, got dressed again, and I made myself a cup of tea, and I'm going to now talk about the physics of what's going on here so that we can really understand exactly why we're getting these little molecules forming. Now, to do this, we've got to zoom in, and I mean really zoom right in. We're looking at the actual air itself, and air itself isn't empty. It's actually filled with billions and billions of tiny little molecules. including the water in its gas form, which is that water vapour. Now, the best thing to think about with these little molecules is they are performing this sort of high energy, totally invisible dance all around us. Now, what does this invisible dance actually look like? Well, it actually all boils down to energy and a whole lot of movement. To help me explain what I mean here, I'm actually going to rely on a television advert back in 2005. Now, this was a television advert to advertise televisions. It was made by Sony, fantastic advert, and I love the visuals in this, which is why I want to use this. It really helps to visualize what I'm talking about with this chaotic thing with all the molecules bouncing around. So whilst watching this, I want you to imagine that it's the tiny water vapor molecules in the air are like millions of the tiny bouncy balls. Now, the air temperature is basically the energy level of the water molecule. And in this television ad, it's actually the gravity that gives them the energy as they bounce down the street. It gives them the kinetic energy. So when the air is warm, or in this case, the balls are higher up the street, those bouncy balls are super energetic. They are just zipping around, bouncing off everything in sight. The walls, the cars, each other. It's a complete frenzy. Okay, so what happens when one of these super energetic bouncy balls actually hits something? It turns out the outcome is totally different depending on what it actually hits. Every single time one of our bouncy ball molecules crashes into a surface, it transfers just a tiny bit of its energy. Most of the time, it's no big deal. It's got plenty of energy left to continue to bounce right off and just carry on its chaotic little journey. But, and this is the key with water molecules, the temperature of the surface it hits changes everything. If a water molecule hits a warm surface, it's kind of like that bouncy ball hitting a hard surface. It loses hardly any of its energy and it just springs back into the air. But if it hits a cold surface, it's more like hitting a patch of wet sand. That cold surface just sucks a whole bunch of energy out of it, and suddenly the molecule doesn't have enough power to break free anymore, and it gets stuck. Now, one single molecule getting stuck, you're never going to see that. But when millions and millions of them slam into that same cold surface and they all get stuck, they start to clump together. In this video clip, it's like when the balls reach the bottom of the hill. They've now lost their kinetic energy or their speed energy from the hill, so they've now slowed right down and they've all clumped together. And when water molecules do that, they change from an invisible gas, that water vapour, into something we can actually see. They clump together to make liquid water. And that, my friends, is condensation. It's such a fun video that. It's worth going and finding it on YouTube. In fact, there's a making of as well, which is really interesting as well to watch. But that aside, what we're now talking about then is when these molecules have got to that tipping point of where they've cooled to such an extent they're clumping together and now forming this liquid. Now, of course, science has a name for it, and that brings us to the whole point of what this video is about, which is called the dew point. The dew point is basically the temperature where the air is 100% full. It's completely saturated with water. It just can't hold any more. And what's interesting is it's not one specific number, and it actually changes. The more moisture that's in the air, the higher the dew point temperature is. But the rule is that always the same, that if the surface temperature drops below that dew point temperature, you're going to get condensation. It's just an absolute guarantee. Okay, so now we've got the science down, let's circle all the way back to that foggy mirror at the beginning of this video. Here's exactly what's happening step by step. The air inside the bathroom is warm and it's full of those energetic water molecules from the showering. Meanwhile, the mirror is cold, or at least it's at room temperature. And because the temperature of the glass mirror is below that dew point temperature of the indoor air, it becomes the perfect trap. The bouncy balls inside hit the colder glass. They lose all their energy and they get stuck, and boom, you've got this foggy window. Now, don't just take my word for it. This is a fundamental principle in building science. It's a totally predictable physical reaction. You take warm, humid air and you put it in contact with a cold surface like glass, you're going to get condensation. Now, what I'm going to cover is how we determine where that crossover point is, i.e. the temperature at which condensation occurs, the dew point temperature, how we find that temperature in this next bit. Now, we're at 20.1 degrees C and 51% relative humidity. Now, these should mean something to you if you watch the other video to understand the relationship between the two. How do I know what the dew point temperature is. In other words, the temperature at which this would reach 100% humidity, i.e. we'd start seeing some condensation. Now, this is a question that many, many years ago, engineers asked. And the engineers asked those questions not out of one of comfort, but actually because it was all about control. And this is the fundamental principle of what we call psychrometric charts and where they originated. Now, this bit is going to be a little bit of a history lesson on psychrometric charts, so bear with me, but here I'll run through it. Now, why do we even need these psychrometric charts in the first place? Well, it was those engineers that were working on various different machinery or areas where condensation was causing real damage, corrosion, mold, icing, all sorts of issues that are associated with water condensing at that critical point. And guessing just wasn't good enough. They actually needed reliable predictive tool to know at what point at what temperature they were going to get these moisture. So in the late 1800s and the early 1900s, work on thermodynamics and moist air really kicked off. So scientists like Dalton, Clapeyron and others studying gas behaviour and water vapour, they used early wet bulb and dry bulb thermometers to start really building up a picture of what happens when temperature changes to the phase of water, gas to liquid. Now, engineers already understood that air temperature alone was meaningless when moisture was involved. And the real challenge with water is that moist air is really messy. Water vapour doesn't behave like an ideal gas, like a single gas of nitrogen or oxygen, once the phase change is involved. So in other words, once it changes from water vapour as a gas into a liquid, it doesn't react linearly. It has a different components in terms of what's going to happen to it, the pressure, law and temperature changes. So these charts were then built. Thousands of controlled experiments measuring the dry bulb temperature, the wet bulb temperature, relative humidity, vapour pressure, dew point, and the results plotted empirically rather than derived from one elegant formula. Now, actually, in the rise of air conditioning, sort of in the late war and sort of mid to early 20th century, especially in the kind of 1920s onwards after the First World War, the growth of mechanical ventilation and air conditioning systems really started to proliferate. And especially in the 1950s, this is when the charts really started to become standardised and widely published and then taught to engineers. Engineers needed a shared reference that everyone trusted. So what do these psychrometric charts actually represent? Well, for a start, they're not actually a calculator. It's actually more like a map. It's a map of how air and moisture behave together. And it's so powerful because every point on the chart describes a complete air state. From that single point, you can read relative humidity, dew point, moisture content, and heat content from that single point. Now, the critical link to dew point is that it's not a guess. It is baked into the experimental behaviour of air. And why this matters. So these charts reflect real world behaviour, not a theoretical perfection. And because of that, that's why they work so well today. So with these psychrometric charts, there are two ways in which we can stay dry. What I would call strategies to reduce this risk of condensation in your home. And I'm going to cover what those are in this next bit now. Now, I've moved the camera over here and I've got to work quite quickly because my wife gets really frustrated when I move things around for kitchen experiments, and especially when I don't put them back. She's out at the moment, so I'm going to try and do this as quickly as possible. Okay, let's describe the setup. So I've just got a box here, which I'm going to be using later on, and I've got here a scale of temperature. So just imagine we've got 4 degrees, 6 degrees, 8 degrees, 10 degrees, 12 degrees. So imagine that's as you go up, it gets warmer. I've set this horizontal line here using the laser level because if we look at what we've got here in terms of values, we've got 19.8 degrees C and 52%. So I put these into the dew point calculator. So that's going to go 19.8 and 52% relative humidity, 50%. Calculate that. That calculates the dew point temperature in this room at 9.7 degrees C. That's roughly about here. That's why I've got the line on the laser level set up for that. Now I've been into the bathroom and I've pinched some of the shelves from the bathroom. Now these are just quite simply pieces of glass. This has been sat in this room for a couple of hours, so it's pretty much at the room temperature. So it's going to be pretty close to 19.8, roughly 20 degrees. And as you can see on here at the moment, just like the other walls and other surfaces in here, no sign of any condensation. Now what I'm going to do, I'm going to head over to the fridge where I've put another plate of glass, just like this, in the fridge for a couple of hours to cool it down. As you can see straight away, the much colder is below the 9.5 degree dew point, so straight away we've got condensation forming. Now, because I'm a geek, I've got one of these little infrared cameras that clip to the bottom of your iPhone, or in this case, an iPad, just to really show, can you see there, the thermal difference between the two? You can't even see the top one because it's blended in to the ambient temperature. So even if I point it on there, it's about 20 degrees at sort of room temperature compared to the plate that's just come out of the freezer, which is looking at sort of still -2 degrees. And that's why it sticks so dark on there, and that's why I've got the condensation well below the 9.5 degree dew point temperature. Now remember, for this air in here with this humidity, that's the dew point. We've got 9.5 degrees, all dependent on the moisture within the air. We've got this piece of glass which is well below that 9.5 degrees, which is why we've got moisture appearing, why it's got condensation on the surface of it. If I was to heat up this plate, so you put my hand on here, and as you start to warm up this plate, gosh, it's cold, what's going to happen is the bit that I'm warming up here is going to start to come above that dew point temperature, i.e. above that 9.5 degrees. Now, I don't think I've got the patience to hold my hand here, plus I'm likely to get frostbite if I do. But hopefully, as you'll start to see, you can see already a slight heat patch where my hand was. And if we look at the thermal camera, even just briefly holding my hand on there, can you see how you've got my handprint? As you can see, that area there is roughly at 3 or 4 degrees compared to the -1 degrees for the rest of the actual glass itself. So what I'm doing there is by increasing the temperature of that glass plate above the dew point means that we're then going to lose all the condensation forming on that. So that's one method of defeating dew point, making sure the surface temperature is above the dew point, you won't get condensation. Let's go back to this bouncy ball thing. What we're essentially doing is giving these bouncy balls their energy back, or adding the kinetic energy that they bounce down the street with. We're almost taking them back to the top of the hill by adding heat. It means they're not slowing down and clumping together. And that's what we're doing by adding heat to the room. So that's covered raising the surface temperature, increasing the energy that each of the bouncy balls have got to stop them from condensing. The other one is what I covered in the other video, which is about reducing the humidity. So in other words, this is about reducing the number of molecules of water we have in that parcel of air. And I covered that, if you recall, in my first video, where I demonstrated with the two glasses the amount of moisture in a same parcel of air depending on the relative humidity. But I want to bring this all together with regard to what I covered on the first video about opening windows and what we've understood here on dew point. So we've got our hygrometers, and that's given us our temperature of the air and our relative humidity. From that, we were able to then use the psychrometric charts to understand what the dew point temperature is going to be for this air in this particular room. We then look at opening a window, and I covered this in my first video. And one of the questions that I come up with so much is, how long do we need to open the windows for? So say, for example, this room is at 20 degrees, at 50% relative humidity. That gives it around about a dew point temperature of 10 degrees. Now the walls temperature at the moment, they're reading just under 20 degrees. I mean, 17 degrees at the moment. If I was to open that window for 5 or 10 minutes, I will notice a reduction in the relative humidity relatively quickly. Now the balance here, and this is one of the things that's quite tricky to get on a building, is balancing the cold air, dry air coming in, getting the wet air out, but not cooling your surfaces too much. And to be honest, this is teasing to my next video, where I'm going to gather some empirical data and do some experimenting with how long a window should stay open in order to change the air mass, but not cool the room's walls. So make sure you're subscribing to not miss that. So let's wrap this up about dew point and about psychrometric charts, which I've covered. We've got our hygrometers, which gives us the temperature and the relative humidity. We've got our infrared thermometers to measure the surface temperature of the surfaces to ensure that they are never below the dew point temperature, which we've got from the psychrometric charts. We've got our little infrared cameras that you can stick on the bottom of your smartphone to then visually be able to see the cold spots in your room. Now, all of that is doing is understanding where the risk areas are of condensation, but there's a little bit more to it than that with regard to when we're thinking about things like mold risk, because you don't need 100% relative humidity, i.e. condensation to form, for mold to start growing. It actually can be at lower relative humidities. And I'm going to cover that in the next video, because it's all about not just condensation, but all about airflow. And that also comes into how long we need to have our windows open to be able to create the airflow, but not too long that it cools the walls. And that's all coming up in the next video. And I've got some more visualizations doing with a smoke machine, which should be quite fun. Now, thank you ever so much for watching. Appreciate you giving us a thumbs up and sticking any comments or questions you've got in there. Come on. There we go. This is my little pooch Mayday. She's saying goodbye as well. Next time we're going to cover air movement and the risk of mold and what you can do about it, including how long you maybe need to keep a window open in order to get that change of air movement without risking cooling the surfaces too much. That's all coming up in the next video. Thanks very much. See you next time.